So hello everyone. Today we'll be starting with the week 8 of the course Lean Dynamical System, in which we will talk about the observer design and we will see the output feedback control also. So this problem of output feedback, we took this as a motivation when we introduced the concepts of the observability and the detectability, and now we will see that how we can actually achieve this output feedback. So the outline of this week 8 is that we will be discussing about the state estimation algorithm. And in these algorithms, we will discuss two types of design. First is the full order design and second is the reduced order design. Once we come on to the reduced order design, we'll define it first and then we'll go to the synthesize procedure. Second, we will see the feedback from the estimated states. And so both these first point and the second point, we will be focusing only on the single input and the single output case. In the third point, we will generalize the previously discussed results for the multivariable cases. And finally, we will discuss about the unknown input observer, its definition, and also the synthesis procedure for the UIU. So starting with the introduction and motivation about the observability. So if we see let's say we have the plant governed by, I will draw two output, one is the X, another is the Y, and this is the U. So far we have seen the controller design procedure where we are putting the state feedback as to some reference signal, let's say R, by taking directly the measurement of the state variable. Okay, so it was U is equal to R minus Kx. So this is the control signal. K of X. This is the control law. Okay, so in this controller design or the state feedback mechanism, we see that in the control law we need the information about the state variable. Okay, now we had said a number of times that this state variable is an internal variable, and many times it might be possible that this X might not be directly available. Whatever be the, we have only two external signals. External signals by mean to say which the signals which we can measure directly. So these two signals are the input signal and the output signal. So if I still want to design the state feedback controller without using the knowledge of the X, how we can do this? Okay, so in the last week we introduced a concept of observability and the detectability, which helps us to at least ensure that we can design an observer which would give us the estimate of this state variable X. Okay, so now if you recall that we have discussed one procedure also, which is the Gramian based construction of the state signal, and that state variable was actually computed at some time t naught. Okay, so now we will see that how we can compute a continuous estimation of the state X. Okay, so if we go to the precise problem statement, we would consider the n-dimensional state equation where X is a n-dimensional vector and U and Y are scalar, mean to say that it's a single input single output system. So the information which is available to us is, we know all the matrices and the vectors A, B, C is available to us. Since U and Y are the external signal, we also have their knowledge. So the problem we need to solve is to estimate X from U and Y with the knowledge of ABC and UY. Okay, so there is a standard procedure of doing this. So first of all, pay attention to this state equation. Okay, so if we see that the A is known to us, B is known to us, and U is also known to us. What we do not know is only x. So if I want to compute this x, how we can do this? So let's first of all write the equation of this plant. This is the internal description of the plant in terms of u and y. So it is x dot is equal to ax plus bu. Okay. So I would design an observer, let's call it O, where I am taking the measurement only of the U, and since B, A are known to me, so I can construct this one. Okay, so let's write the state equation for this one. It is x hat dot is equal to ax hat plus bu. Okay, so this is my plant, this is my observer. Now the problem is I want x is equal to x hat, right? So if you recall that in the previous week we actually did the construction of this state signal, but that reconstruction was done at a particular time t naught. Okay, so if you recall very quickly that the Gramians provide only the value of the state at a particular instant of time instead of the continuous estimate, and this was the theorem we had discussed, that that given the data during the time interval t naught comma t1, we computed x of t naught as the inverse of the observability Gramian multiplied by this integral, where we need the information of the state transition matrix which we can compute. C is already known to us and y tilde is basically computed by this. So here if you see, we can directly compute y tilde because we have the knowledge of all the matrices and the signals. So this formula was written in the time variant case, but this you can also compute for the time invariant case, right? So if we go back to this problem, what do we need? So first of all, let's see the solution of this x of the plant. So the solution of x, we know that you can compute by e to the power minus at x naught. Okay, this would be the solution of this plant, and the solution of the, let's say, the observer, it is x hat this part would remain the same as it is. Okay, so if this integral remains the same, so the value of this one would also remain the same, but the only change you see here is the value of x naught and x hat naught, because this exponential would also remain is basically the same. So I can write this as x as a function of x naught, okay, and this as x hat as a function of x naught hat. So I know that if x naught become equal to x hat naught, then it implies that I would definitely have x equal x hot for all time t. Okay, and so now if I use the Gramian based reconstruction of this x naught, which I can do, let's say if my data is given from t naught to t1. Okay, now so suppose if I want to do a continuous estimate of the state, what do I need to do? That every time I have to compute this x naught hat by taking the data from t naught to t1. So for example, again if I need a continuous estimate for some another time window, let's say t1 comma t2 or t3 comma t4, then again I need to compute this initial condition x hat of at t3, so that I can ensure that x at t3 is actually equal to x hat of t3. And this if this condition is satisfied, then I would say that x, or let's say this implies that x of t becomes equal to x hat of t for all t greater than equal to t3. Right? So every time if I use this kind of an estimator, or we call this as an open loop estimator also, every time I need to compute this Gramian to compute the value of x hat at that time instant. Okay. Now there is another way of doing the reconstruction also. Say for example, so this is the first point. We'll come on to that a bit later. That there are some disadvantages in using that open loop estimator. That the initial state must be computed and set each time we use the estimator. Otherwise, it won't be possible. The pure estimation. Now let's say we have these two equations of the plant and the observer. Let's rub this a bit. Okay, so here I will define an error signal E as x minus x hat. Okay, we define this signal E, which we call the error between the actual state and the estimated state. So on taking the derivative of this error, I would get x dot minus x hat dot. So from these two equations, I would substitute this x dot and x hat dot, and finally I would have ax plus bu minus ax hat minus bu. So you see that this bu part get cancelled out and the remaining part is ax minus x hat, which is nothing but ae. Okay, so we have discussed this number of times that this now becomes a homogeneous system even if there is a mismatch between x and x hat at any point of time. Okay, and if this A matrix, if the eigenvalues of this A matrix are on the left hand side, then we can say the error between the state and the estimation of its estimation would go to 0 as t tends to infinity. Okay, but the extra condition we need to put here that A should be a stable or Hurwitz matrix, which again might not be possible all the time, because if A is a, say for example, if you are computed the x hat at some initial condition by using this Gramian and you put it here, then what would happen, we have already seen that in that case x would become equal to x hat. Okay, so this part would go to 0, again you would have E dot is equal to 0, right? But there could be some external disturbances or some uncertainties due to which this difference might not be 0 all the time, even if you have used the Gramian based reconstruction. So because of the non-Hurwitzness of this A matrix, your error will go towards to the infinity, right? So this is the second disadvantage that if the matrix A has eigenvalue with positive real parts, then even for a very small difference between x of t naught and x hat of t naught for some t naught, which may be caused by a disturbance between these two state trajectories, and finally the error will grow with time. Okay, so now we will modify that open loop estimator by introducing this term. So this state equation we had already seen, which is the open loop estimator. Okay, now in this open loop estimator I added this term where I have introduced a vector L multiplied by the output signal minus, you can visualize this as y hat, which is Cx of it. Okay, y minus y hat. So I introduce this term, and this introducing this term will uh, bring some advantages to the estimator. So if I see its construction, so this is the plant again. Now I have written it into the by using the complex variable s in the frequency domain. So if we do not have this part L C here, so in the open loop estimator we were using this part and only this part. Okay, so now by introducing this term into the open loop estimator, basically I have introduced a feedback mechanism into the observer itself by introducing this vector L. So this figure is basically the implementation of this equation. I can parameterize this equation to uh, extract some nice features of this introduction. So after parameterizing, so what I have done, so once you replace y hat by cx hat, I can club this term and this term. So I would have a minus l times c with a common factor x hat. This term comes as it is, and similarly this term appears as it is. Okay, this I have done so that I could get the modified state matrix, and this state matrix would be now A minus LC, right? Because this U and Y would now appear as a input to this system, and this is the block diagram representation of this equation, which we call the state estimator. Okay, so we'll see what are the benefits of using this feedback mechanism in the observer itself. Again, we will introduce this error signal as the difference between the actual state and the estimated state. So using the same procedure, I will differentiate E and then substitute the plant equation and the estimator equation into this, and finally obtain basically x dot minus x hat dot. So x dot is only this part and x hat dot is this one, which is the parameterized one which we had seen in the second figure. Okay, a minus lc x hat minus bu minus lc x of t. Okay, so I will start clubbing the terms. That see here we have a. First of all, we'll rub this so that there is no confusion. So first of all, we take this term a and minus lc, taking a common factor x. Again, this a minus lc we keep as it is. Okay, and this part bu part will get cancelled out. So the remaining part, if again taking the factor a minus lc common from this, we will get a minus lc times xt minus x hat. Or I can represent E dot is equal to a minus lc times ec, and this equation governs the estimation error. Okay, so there is a clear difference in the error equation of the open loop estimator and the closed loop estimator. In the open loop estimator, let's note it by open loop, we got E dot is equal to a times E of t. Okay, and in the this is the closed loop estimator, where this A matrix is now modified to A minus L times E. So it says that if all the eigenvalues of A minus LC can be assigned arbitrarily, then we can control the rate for E of t to approach 0 and equivalently for the estimated state to approach the actual state. Right? We only need to ensure that the eigenvalues of A minus LC is on the left hand side. Now, even if there is a large error between the initial conditions of the actual state and the estimated state at some time t0, the estimated state will approach the actual state rapidly now. Okay, thus there is no need to compute the initial state of the original state equation. So with this introduction of the uh, additional term, which is L times y minus y hat in the open loop estimator. We got rid of those two disadvantages which we had seen in the open loop estimator. So let's try to formulate it now. So this was the original equation by the addition of this term, and this is the parameterized one which we called it the state estimator. So this result says that consider the closed loop state estimator, this one, if the output injection matrix gain L. Now we also call this output injection because, okay, we can see it here, that we made the output appear into the state equation itself, okay, through this vector L. So we call it the output injection matrix gain L, or we can call it a vector also, makes A minus L times C a stability matrix. Then the state estimation error E of t converges to 0 exponentially fast for every input signal U of t. Okay, we call it for every signal because we had seen here that the influence of the U signal onto the error signal is nullified or get cancelled. That's why. So we can put any U, the state estimation error would not be affected. Okay. And the proof of this we had already seen, that how we had approached to the state error dynamics of the observer. Okay. So note that the correcting term L y hat minus y or y minus y hat is used to correct any deviations of x hat from the true value x. So when x become equal to x hat, we would have y become equal to y hat, and this term also disappears. Okay. So the only resting part is this plant and this state equation, which is nothing but the plant equation, because we actually want x equal x hat. So though we had reduced some of the disadvantages we had seen in the open loop estimator, and we had seen that if this we can ensure, or if there is or let's say if A minus LC is a stability matrix, then the error will converge towards to 0. But there are further questions which arises after that formulations. So first of all, we need to answer, does there exist a vector L? Right? Because if there does not exist a vector L, you cannot introduce that term. And if you cannot introduce that term, your observer would still be an open loop observer. The second, if we have ensured the existence of the L, we need to compute the L. The third point, that under what conditions we can say that A minus LC is a stability matrix. Fourth, that can the eigenvalues of A minus LC be placed arbitrarily, or under what conditions we can say that the eigenvalues of A minus LC be placed arbitrarily. Now this is related to the third part, the fifth one, that can the eigenvalues of A minus LC be placed at least on the left hand side of the complex plane. Okay. Now there are further questions also which we will see as we go ahead into the lectures. So first of all, we will see one of the key results which ensure the existence of this vector L, and it has some connection with the observability which we had discussed in the 7th week. So consider the pair A comma C. All eigenvalues of A minus LC, or this modified matrix or the error matrix, can be arbitrarily assigned by selecting a real constant vector L if and only if A comma C or this pair is observable. Right? So we can see a quick proof that this theorem can be established directly or indirectly by using the duality theorem, which we have introduced last week also on the 7th week. So it says that if this pair is observable, so we know that the observability of this pair A comma C is equivalent to saying that this pair A transpose comma C transpose is controllable. Okay. Now the controllability of this pair A transpose comma C transpose implies that all eigenvalues of A transpose minus C transpose K can be assigned arbitrarily by selecting a constant gain vector K, and this is nothing but a state feedback controller design. Okay, so this result is taken from that week. Now if I take the transpose of this matrix which I got by introducing this vector K, I will get A minus K transpose C. Okay, now you will notice that this A minus LC is equivalent to A minus K transpose C if we have L is equal to K transpose, right? And K we know already, we have designed by using the state feedback design procedure. Okay? So the procedure for computing the state feedback gains can be used to compute the gain L in the state estimators. Right? So with this theorem, we have ensured we had guaranteed two things. First, that there exists an L, and under this condition that the pair A comma C is observable, this L would definitely exist. And at the same time, we have shown that how you can compute the L. Okay, by using the procedures we had discussed during the state feedback controller design. So we can quickly see those results. So one of the method you would see or you would recall is the eigenvalue assignment approach. So the following results can be obtained by duality from the eigenvalue assignment that we proved for controllable and stabilizer systems. So first we discuss the, or let's say first we see the observable case, that assume that the pair A comma C is observable. We need the observability, otherwise there won't exist any L. So assume that this pair is observable given any set of n complex numbers lambda 1 to lambda n, there exists a state feedback matrix L such that A minus LC has the eigenvalues equal to the lambda I. Right? So this result ensures that given any eigenvalues we can design or there exists this L such that the eigenvalues of this matrix becomes equal to the given these complex numbers. Now if we have a weaker condition than the observability, which is the detectability, so let's say if the pair A comma C is detectable, it is still or always possible to find the matrix L such that A minus LC is a stability matrix. Okay, so under both the cases, either the pair is observable or the pair is detectable, there would always exist an L. Okay, with this observability we get some additional freedom that we can place any eigenvalues to the desired location, but with the detectability we at least ensure that the this error matrix would be a stable matrix. Okay, and we had discussed the method of computing this where we have assigned the eigenvalues, right? So you can see that method for computing this vector L in a similar way when we had designed the state feedback vector. Okay, the second method, if you recall, is the Lyapunov equation method that consider this n-dimensional state equation or the pair A, B, C, which we have labeled as the CLTI. So the first step, in the first step we need to select an arbitrary n cross n matrix F that has no eigenvalues in common with those of A. Okay. Second, I can arbitrarily select a vector L, ensuring that whatever the matrix F I have selected arbitrarily in the first step paired with the vector L is controllable. Okay. Now using this Lyapunov equation, I will solve for the unique T, which is T A minus Ft is equal to LC. So then the state space equation, which is given by Z dot is equal to Fz plus TBU plus Ly would be the internal state of the observer now. Okay, and x hat would become the output of the observer. So x hat is equal to T inverse Z. Now we know from the Lyapunov equation that whatever the T we would get, it would be a non-singular. Okay, so this is one state space system with the state equation and the output equation of the plant. With this Lyapunov equation method, by following these three steps, we can write another state space system for the observer whose internal state is Z and the output is x hat, and this x hat would be equal to x, right? So we can quickly see that whether the whatever the observer we we got by using that Lyapunov equation method is actually a or would lead me to the state estimation error equal to 0. So here we'll define the state estimation error as equal to Z minus T times X. Okay, where Z is the internal state of the observer and X is the original of the plant. So defining this and following the procedure, the similar procedure that we get, we first of all take the derivative of this error. So we will get Z dot minus T X dot. Then here I will replace this Z dot and X dot by their respective equations. So Z dot is basically Fz plus TBU plus LCX or Ly, and T times X dot. So T would be pre-multiplied with this complete equation, which is AX minus BU, which is X dot. Right? So again I will start pairing the terms. So the first term will come as it is. Similarly, this I wrote this as a second term, LCX. So here you would see again that the influence of the input has been cancelled out completely onto the estimation error, on the error dynamics. Okay, so whatever the observer we have synthesized here, again it would be the state estimation error would be 0 for any u, right? But still we need to show that the state estimation error goes to 0. Okay, now by using this Lyapunov equation, we have replaced this TA part by Ft plus Lc. Okay, because if you see that the Lyapunov equation is TA minus Ft is equal to Lc, so this term we got in the error dynamics and I am replacing it by Ft plus Lc. So this TA has been replaced by Ft plus Lc and times Xt. So all the terms we had seen. Now you would see that this term LCX again got cancelled, and the remaining part is Fz minus Tx, which is nothing but my F times E, which we have defined earlier, Z minus Txt. Okay, now if you, in the design procedure itself, we have ensured that F is a stability matrix. So if F is stable, then for any E of 0, the error vector E of t approaches 0 as t tends to infinity. The Z approaches to t of xt, or equivalently t inverse Z is an estimate of x. Okay, and this was the observer basically, t inverse Z.